Good evening, everyone. I hope I am audible to you all. Can anyone confirm whether I am audible?
Yes, ma'am.
Yeah. So, once again, welcome everyone. So, this will be our second session of live problem solving. So, before I move on to that, last time one person named Rathika, yeah, she had messaged me regarding a query on GATE. So if you are present, but when I replied, I couldn't get the exact. The name is Rathika. She had mentioned me some. She wanted few details regarding GATE examination, but she didn't reply to my question. So if Rathika is present, please unmute and speak. She has not yet joined, maybe, so I'll ask again at the end of the session then. So I think we can start today's session then. So I hope my screen is visible. So on that note, let us start today's session. So welcome everyone once again to the second live tutorial session on fundamentals of electronic materials and devices. So last Tuesday we had a course and we had a similar session where we had seen problems pertaining to the first week. So in this week we will be seeing questions related to contents on the second week. So once again, I introduce myself. I am Sandra Krishnan P. So last week I had mentioned, so I am doing this as a duty with respect that I have to complete this for my DMR of tenure. So for people who weren't present last week, other than the questions that we are discussing here, if you have any queries related to NPTEL, you can either post in the discussion forum or you can mail me at sandra.pmrfid@gmail.com. So people, in case you have a request like you want particular content to be repeated in class or you have any question that you're facing difficulty with, so I'll be able to help you on that. But at the same time, please note that in case you are discussing a question which is present in the assignment, in that case I will be solving that particular assignment question only once the deadline has passed. So I hope I'm clear on that. So people who want, please take a note of my email ID. So with that, I think we can move on to today's questions. So while doing the questions, once again, I say you'll be given sufficient time. Try to work out the questions here and now itself so that it will be a practice for you when you're writing your assignments as well as for your final examinations. So please try to work it out, and when asked for, please unmute and speak. It's not like a question answer session or you'll be evaluated based on this. It's just like an interactive session. So whatever doubts you have, please unmute and speak. And at the same time, when you are asked for an answer, please try to respond. Yeah. So with that, we'll start today's question. So a simplified energy band diagram of an intrinsic semiconductor at thermal equilibrium, that is 300 Kelvin, is shown. In the accompanying table, which one of the four columns correctly represents the listed parameters? Assume the same effective mass for electrons and holes. So here we have been given a diagram, which is the energy band diagram of an intrinsic semiconductor. So intrinsic semiconductor, as you all know, it's an unknown world. It is at thermal equilibrium. So in that case, in the second week, you might have come across terms like electron on affinity, band gap, work function, etc. And you have given the nomenclature for two energy levels is also given. So here it is delta E1, here it is delta E2. So combining these two, that is by relations of delta E1 and E delta E2, you have to find out which of it represents band gap, which of it represents electron affinity, and which of it represents the work function. So first try to memorize or try to recall the definitions of band gap, affinity and work function, and using that try to arrive at the particular relation for these three terms. So I hope the question is clear. The question is clear, right?
Yes, ma'am. It is clear.
Yeah. So please try to work out. one person has mentioned that they think that column 1 is correct. Okay, we'll wait for the others. So please try to unmute and speak, otherwise I'll have to keep switching between the windows. So okay, one person has mentioned it could be column 2. So there are two opinions now. One person thinks it's column 1 and or the other person is column 2. So what about the others? What are the answers that you are arriving at?
Ma'am, column 2.
Okay, one more answer on column 2. And what about the others? Let's take a few more minutes and then I'll go with the answer. Yeah, so I think it's okay. Again, one person has mentioned it could be column 1. So we are like fluctuating between column 1 and column 2. So let us move on to the answer. So before we move on, like, can anybody unmute and tell me what is meant by the band gap? Like one person can tell me what is band gap, and other people can talk about electron affinity and what is work function. So can someone define band gap?
Band gap is the distance between the valence band and conduction band, energy in
Energy
between them.
difference. Okay.
Yes.
And what is electron affinity then?
Then electron affinity means
Yeah. If you have notes, you can check your notes. That is
yes,
also
ma'am.
fine. Yeah. Like band gap, as she mentioned, it is the energy difference between the valence band and conduction band. And what is electron affinity? Anyone else?
It might be the energy difference between the vacuum level and the conduction band.
Okay. And find the work function.
Uh, uh,
It is similar to the electron affinity, but not the
yes,
same.
ma'am.
Yeah. So
Uh,
what is the clue?
phi value to find.
Yeah. So basically, it's the energy required to remove the electron from the surface of
Uh,
semiconductor to the vacuum, right? Yeah. So in that case, we will go on to the answer. So basically, these are the terms that we come across. So first, suppose we have an energy band diagram like this. So this is the conduction band maximum, also known as the lowest occupied molecular, unoccupied molecular orbital. Then we have the valence band maximum, that is the highest occupied molecular orbital. So at it is mentioned that it is an intrinsic semiconductor at zero. Therefore, we would be having electrons at this level and the conduction band will be completely empty. So for normal semiconductor solids, we go for the terms valence band and conduction band. So here is the valence band maximum, this particular energy. Here is the conduction band minimum. So another terms, when we are going to molecular solids, what happens is that instead of bands, we will go into energy states. So in that case, we will talk about the HOMO and LUMO. HOMO means highest occupied molecular orbital and LUMO stands for lowest unoccupied molecular orbital. So that is the edge of the energies. So as you mentioned, the highest energy level, and one more thing that we'll define now is the highest energy level that the electron can occupy at absolute zero temperature is known as the Fermi level. So at absolute zero, there is no thermal generation of carriers from the valence band to conduction band, but in that case also some amount of carriers will exist at the maximum energy. So this maximum energy is known as the Fermi level, and Fermi level always lies between the valence band and conduction band. And here all the electrons will be in their lowest energy state. So next is band gap or energy gap. Band gap or energy gap, as the person rightly mentioned, it is the energy difference between the VBM and the CBM. That is the energy difference between the valence band maximum and the conduction band minimum. So an electron can move only from this valence band to conduction band if an energy equal to Eg is supplied. So suppose we want to move an electron from this valence band and we have to push it to the conduction band. So an energy which is at least equal to Eg has to be supplied for this movement to take place. So next is work function. Work function is another property of material which is defined as the energy that is required to remove an electron to infinity from the surface of the solid. That is the work function. So we can say that at absolute zero temperature, the electrons will be residing at the Fermi level. So from this Fermi level, we have to remove the electron to the vacuum level. So that is the work function of the material. So next, energy difference labeled as psi between the bottom of the conduction band and the vacuum level is known as the electron affinity. So here we will be removing from the surface, but the other case when we are removing this particular electron from the conduction band minimum to the vacuum level, it will be termed as electron affinity. So I hope the definitions are clear. So now can you think again whether option 1 or option 2 is correct? So it was given here that these and delta E1, that is these two energy Fermi level is given. So Fermi level is given meaning that this is the conduction band minimum, this is the valence band maximum. So in that case, delta E1 will be our work function. So band gap. So we have two options, that is either it can be column 2 or it can be column 4. So now we have to check out the other two things, electron affinity and work function. Work function, as we already said, it is removing from this particular Fermi level to vacuum. So Fermi level we can write as delta E1 by 2 right here, because the Fermi level lies exactly at the center. So delta E2 minus delta E1 by 2 will be your work function. Am I correct? So band gap, we told it is the difference between HOMO and LUMO, or conduction band and valence band. So if you are removing from Fermi level to vacuum level, it is known as work function. If we are removing from this particular region, it is known as electron affinity. So can you think again now? So which option will be correct? So band gap everyone knows. Between conduction band and valence band is delta E1. So directly it will come as delta E1. So it
Column
can be
2 will
2
be
or
correct.
4. Yeah. Hello, somebody unmuted. Can you speak again?
Column 2 will be correct.
Column 2 will be correct. Yeah. So basically, so you have to be careful. Difference between conduction band and valence band is the band gap, that is delta E band directly. So next is removing an electron from the Fermi level to the vacuum level. That is the work function. Here Fermi level lies at the center of delta E1. So Fermi level lies at delta E1 by 2. So this is delta E1 by 2. This is delta E1 by 2. So suppose we want to remove from this dotted line till the vacuum level, we have to, what we have to do, delta E2 minus delta E1 by 2. That is delta E2 minus delta E1 by 2. Similarly, if we are removing from this conduction band minimum to infinity, means that it is the electron affinity. So in that case, here it is delta E2 minus delta E1, which is delta E2 minus delta E1. So all these three are correct in column 2. So the answer will be column 2. So is that clear for everyone? Yeah, is that clear? Anybody has any doubt? Any doubts, anyone? If not, we can move to the next question. Anyone? Any doubts, or shall I move to the next question? Hello?
Shall we move on? Shall we move on to this?
Yeah. Okay. So we can move to the next question. Okay. Which of the following best describes the relationship between carrier concentration and band gap for an intrinsic semiconductor? So we have the relationship between carrier concentration and, so intrinsic semiconductor, we know that is there is no doping, there is no additional charge carriers, etc. So what is the relationship between carrier concentration and band gap? Is it a linear relationship, reciprocal, parabolic, exponential, or somebody is correct answer is one person has mentioned. Answer is option D. Okay. What about the others? What are your thoughts? If you know the relationship that connects Eg and your carrier concentration N for intrinsic semiconductor, so there you'll be able to get, is Eg raised to something, is it raised to a root, or is it raised to a negative root, or something that connects Eg and N should be there.
Exponential, ma'am. Exponential
Okay.
relation.
So two people have mentioned exponential relationship. We'll see why. So intrinsic carrier concentration is basically given as Ni is equal to root of Nc Nb e power minus Eg by 2 Kb into T. So we know Nb are the density of states in the conduction band and valence band. Then we have e to the power of minus Eg, that is your band gap, and 2 times Boltzmann constant into temperature. So basically the relationship between, if you are considering everything else as constant, Ni will be proportional to e to the power minus Eg. So they will be having an exponential relationship. So is that clear? Yeah. It's directly from the equation. Yeah, one more person has mentioned as option B. Okay. So I hope it's clear. Basically, from the directly from this particular equations itself, you will be able to understand. And for examination, very few equations you might have to memorize, but most of the prominent equations will be given to you in the formula sheet. So you need not memorize, but then to be attentive of what these terms are. So whenever you are solving problems, you might have the formula sheet with you, but you should remember what is Ni, what is Nc, what is Nv, or what is particularly asked in the question, etc. Even though you have the formula sheet, be familiar with the equations and the terminology as well as the constant values, how to convert the constants into SI, etc. All these things you have to be careful. Yeah. So with that, I think we can move on to the next question. Which of the following statements is true? Not that more than one answer may be correct. Addition of trivalent impurities creates many bound electrons at high temperature. Mobility decreases because of lattice scattering. Increase in carrier concentration results in decrease in semiconductor resistivity. Amphoteric dopants always act as donors. So we have four statements. Out of these four statements, which have to tell which one is correct. And sometimes it might be that more than one will be correct. So one is addition of trivalent impurities to a semiconductor creates bound electrons. At high temperature, mobility decreases because of lattice scattering. Increase in carrier concentration results in decrease in semiconductor resistivity. Amphoteric dopants always act as donors. So you can brush through your memory, or if you have notes, or if you want to have any sources, just give me your views on which of these will be correct and why. Check the answer. Others also try to answer. So somebody has answered. Higher carrier concentration means more charge carriers available to conduct electricity, thus decreasing the resistance or resistivity. So I think option C is correct. So one person has mentioned that option C is correct. Okay. Others, please come up with your answers. One person has said that increase in carrier concentration results in decrease in semiconductor resistivity. Okay.
And then option B also I think correct, but
Okay.
I'm not sure.
Okay. One person has mentioned option C is correct, and along with that, option D is also correct. Right. Okay. Okay. We'll see the answers now. So answers are option B and C. So basically, one is at high temperatures, mobility decreases because of lattice scattering. So what happens is that whenever we are increasing temperature, we know that the amount of carriers, that is heat generation will take place, which results in photons, and as a result, what happens? More carriers will be created. But at the same time, the amount of collisions that these carriers will undergo will also increase, and these carriers will also collide with the lattice of the material, and as a result lattice scattering also takes place. Therefore, when temperature goes to a very high value, actually it lowers the carrier mobility because of the scattering phenomenon. Then C, as the question directly mentions, semiconductor conductivity is directly proportional to carrier concentration. So more carriers means more conduction. So amphoteric dopants, it's the name amphoteric dopants means that if you are adding an amphoteric dopant to a material, depending on the group of the material or the valence state of the material, that dopant can act either as a donor or as an acceptor. That is amphoteric dopants. So trivalent impurities means that if you are considering the case of silicon, trivalent impurities means that it will create holes. Therefore, it won't create bound electrons. That is why A and B are incorrect and B and C are correct. So is it clear for everyone? At high temperature, lot of scattering, number of carriers will increase, but the amount of collisions that these carriers undergo with the lattice also increases. This results in lattice scattering, and because of the lattice scattering, mobility will decrease. Then carrier concentration is higher, means that conductivity will be higher, resistivity will be lower. Amphoteric dopants can act both as acceptors and as donors, depending on the valence state of our initial material. And trivalent impurities means that it will be having only three valence electrons, and in case of silicon semiconductor or mixed semiconductors, it will not create bound electrons. So that is why A and D are incorrect and B and C are correct. So okay, I put here some information. Okay. So one person had option B is correct, another person had mentioned Satish. So he has mentioned that as the lattice vibration with high temperature makes low probability of scattering, this reduces mobility. That is correct. Yeah. So I hope we can move on to the next question. Degenerate semiconductors generally exhibit dash. Not more than one answer might be correct. One is very high level of doping, no change in hole concentration, change in temperature, Fermi level inside the valence bar conduction band, dopant atoms with negligible interactions in semiconductor host lattice. So I want all of you to read, just try to find out from your notes or from any other source what is degenerate semiconductors. If you know what are degenerate semiconductors, you will be able to know the answers. And one more way of answering such question is that you can eliminate the wrong options first. So what are degenerate semiconductors?
Option A, ma'am, a very high level of doping.
Yeah, and yeah, anybody else? Any other answers? Yeah. So in that case, so basically degenerate semiconductors are the class of semiconductors which have been doped to a very high extent such that they essentially start behaving like metals. We know that in metals there is no distinction between a conduction band and valence band, rather a sea of electrons which can be neutrally used by any human. So similarly, degenerate semiconductors are doped in such a fashion so as to induce them into behaving like a metal. So basically, they have a very high level of protein. That is correct. So no change in hole concentration with change in temperature is wrong or right. It's basically wrong because in here also we are inducing, like we are adding dopants, we are changing. Like with respect to temperature, there will be more generation of carriers. So whenever there is more generation of carriers, they will leave an equal number of holes in the valence band. So option B is wrong. Next is option C. So we mentioned that there will be a very high level of doping. So because of this doping, we know what happens whenever at absolute zero, the Fermi level will be located halfway between the valence band and conduction band. But whenever we are adding more and more dopant, suppose it is the N-type dopant, the Fermi level moves towards the conduction band. And if it is a P-type dopant, the Fermi level start moving towards the valence band. So Fermi level can actually fall inside the conduction band or valence band. That is also correct. Next is dopant atoms with the negligible interactions in the semiconductor host lattice. That is always wrong because whenever we are introducing dopant atoms, these dopant atoms undergo interactions with the semiconductor host lattice. So typically dopant concentrations will be in the range of parts per billion or parts per billion, etc. And these are non-degenerate, our normal semiconductors. But when the dopant concentration goes so high, the energy levels start overlapping. That is why they start behaving like metals. And here the dopant concentration will be somewhere in the range of 10 to the power 19 to 10 to the power 20. And these energy levels start merging with the conduction band and valence band, and that is the reason why the Fermi level gets pushed. So that is why options A and option C are correct. Option B is wrong because keep in mind whenever there is a change in temperature, an increase in temperature, for example, will create more electrons to go from valence band to conduction band, and equal number of holes will be left behind in the valence band. Similarly, whenever we are introducing dopant atom, what happens with that? It will have interactions with the semiconductor host lattice. Therefore, for this particular question, option A and option C are correct. I hope it's clear to all of you. So let us move to the next question. So this is a problem. So I want every one of you to try to solve it. So basically, band gap of intrinsic gallium arsenide semiconductor is 1.43 electron volt. Electron affinity Psi value is given as 4.07 electron volt. Assuming that effective masses of electrons and holes at the band edges are equal, what is the work function of the material? So in the first question, we had seen what is band gap, what is electron affinity, what is work function, etc. So you have to use that idea. Like suppose it is the difference between valence band and conduction band, that is your band gap. Suppose it is the work function, it means that you have to remove from Fermi level to vacuum. Suppose it is electron affinity, you have to remove from conduction band minima to vacuum. So using these three concepts, you have to find out work function of your material. Band gap is given to you, electron affinity is given to you. So if both are given to you, then how to find the work function of the material? That is the question, and your answer should be electron volt. So everyone can start solving. Everyone using the same ideas that we had followed up in the first question. Please try to solve this first numerical. So once you have got the answer, everyone either you can put it in the chat box or you can unmute and tell me. Let me check if somebody has already posted something here. Okay. The previous question, many people had answered. So yeah, this is the reason why I asked you guys to unmute because okay, one person has answered 4.78 electron volt is the answer. What about the others? One person has given 4.78 electron volt. Another person is giving 2.64 electron volts. Okay, so that is kind of contradicting. So let's see who is correct. Okay, 4.78 and 2.64 are the answers that we got. Okay, others. Okay, let's see if any other answers are there. Okay, 4.78. Okay, that went ahead. Sunil has mentioned the how he got 4.07 plus 1.43 divided by 2. Okay, so then let us check out the answer. So basically, we may remember that electron affinity is removing from this particular level to the vacuum level, that is conduction band minima to vacuum level. Again, work function is removing from a Fermi level to vacuum level, and band gap is the difference between valence band and conduction band. Okay, here the band gap is given as 1.43, so it is intrinsic in nature. Assuming that no temperatures are given, let us assume that it is at equilibrium, that is band gap at the center will give us the Fermi level. So 1.43 by 2 will give us the Fermi level. So that is there. So 1.43 is the band gap, half of it will give us the, okay, now electron affinity is 4.07, electron affinity, that is from this point to this point is 4.07. So now we have to find the work function. Work function basically this to this entire thing. So basically it will be electron affinity, that is 4.07 plus half of 1.43. Yeah. So is that clear? 4.07 plus half of 1.1.43 divided by 2 is 0.715 plus 4.07. That is one way of solving this. Another way of solving this is using the equation. That is, we know that Fermi level, when it is in between the conduction band and valence band, we have two equations using the valence band and conduction band. So basically EV plus half Eg minus 3 by 4 KT ln ME by MH. This ME by MH they are giving because in the question they are telling that the mass, effective masses of electrons and holes are equal. So what happens in this equation is this whole term gets cancelled because this becomes mass equal. So Ln1 will be 0. This entire thing goes away. So basically we are left with only the first three terms, that is EFI, EV and half of Eg here, or EFI, EC and half of Eg here. So using that we can solve. So basically what happens, EC minus EFI becomes Eg by 2 plus 3 by 4 KT ln ME square by MH square, and when you solve that it becomes 7.715 EC minus EFI, that is conduction band level minus intrinsic conduction band level minus intrinsic Fermi level, that is this small region between EC and EFI we get as 0.715. When we add that 0.715 to our electron affinity we get the work function. That is one way of solving it using equations. Another way of solving it is directly using logic, that is here temperature is not given, so we are assuming it to be at absolute zero. At absolute zero your Fermi level will lie between your conduction band and valence band, so it will be at the center of this. So basically at half of 1.43 we have EFI. So this particular distance, that is EFI minus EC, will be half of 1.43, and that half of 1.43 when added to this electron affinity will give us the work function. So either you can go for the logical way or you can use this particular equation for solving. So is that clear to all of you? Okay, somebody has just texted. Yeah, yeah. Surya Teja has mentioned same way. Venkataswaran has also mentioned same way. So either you can use the equation or you can look for logic. That is up to you. Yeah. So I hope it's clear now. With that, let us move on to the next question. Two semiconductors X and Y have same effective density of states both at the conduction and valence band at this. So Nc and Nv for two semiconductors are same. So XNB and XNC is same. Then for Y also YNC and YNB same. Intrinsic carrier concentrations, that is Ni at 300 Kelvin, are given as 2 into 10 to the power 13 and 10 to the power 10 centimeter inverse respectively. If band gap of X is 0.7 electron volt, find the band gap of Y. So basically we have EGX we have to find out EGY. So from this equation, what all things are there? You have temperature with you, you have intrinsic carrier concentrations Ni with you, and then you have Nc and Nv with you. So if you remember, we had seen an initial equation, right? Ni is equal to root of NcNv a to the power minus Eg by 2 times Kv into T. That is the equation you have to use here. For x you will get an equation, for y you will get an equation. So while clubbing these two and then substituting all the given values, you will get the band gap of y. So that is your hint. Use the equation for Ni, which connects Nc, Nv and band gap. So write down both equations and they have same effective density of states. That is where you can equate both of them. So using that you will get the band gap of y. So everyone please start working out. If somebody has responded, we'll go there. Is that option B, 1.1 electron volt is mentioned. Okay, what about the others? Let the others also solve. 1.1, one person has mentioned 0.7 is correct. Okay, and he mentioned option B. Option B again. Then Y is approximately 1 electron volt, which is option B. Okay, many people have mentioned option B. So let us check out. So this is the equation I mentioned. Ni is equal to root of NCNV e power minus Ag divided by 2 times Kb into T. Let x be 1, y be 2. That is the name I am taking. So Ni1, Ni2 is given to you. 2 into 10 to the power 13 and 10 to the power 10. And Eg1 is 7 electron volt. We have to find out Eg2. Nc is given in equal in both cases. So I am writing Ni1 by Ni2. So NCNV part will get cancelled. So Ni1 by Ni2 is equal to e to the power minus Eg1 by 2 times Kt in both cases. So while substituting, 2 into 10 to the power 13 divided by 10 to the power 10 becomes Eg1 by 2 into see here I am substituting everything in terms of electron volt itself. Therefore that is why I am using K as 8.617 into 10 to the power minus 5. That is the reason. So if either I have to substitute both of them in joules or I have to substitute both of them in electron volts. So here I am substituting 0.7 as the electron volt itself. That is the reason why I am taking Kb as 8.617 into 10 to the power of minus 5. So what happens? Yeah. So basically my e to the power minus Eg by 2 times Kb into T becomes this upper constant value divided by this becomes 2000. So basically Eg to the power minus Eg by 2 times Kb into T becomes one particular value. So then we have to take ln on both sides. So what happens? Minus Eg by 2 times Kt becomes minus 21.14, which is approximately 1.1 electron volt. So I hope this is the way everyone substituted. The answer is 1.1 electron volt. So yeah, many people have given as option B 1.1 electron volt. Basically all kinds of such equative questions, the thing is there will be a particular formula, and wherever they are mentioned that for example here it is the effective density of states, here they are telling that the effective density of states is equal, therefore we are writing the equation in such a way that they both get cancelled. Then using the other given values you will be able to solve, and finally your Eg2 value will become approximately 1.1 electron volt. So I hope that's clear. Just check the chat box. Yeah. Okay, many people have mentioned option B. Yeah. So let us move on to the next question. Given that the effective mass of electrons and holes are 1.1 MeV and 0.55 MeV respectively, find the location of the intrinsic Fermi level at 300 Kelvin. The rest mass of an electron and band gap, where Me is the rest mass of an electron and band gap of silicon is 1.1 electron volt. So effective mass of electron and hole is given as 1.10 MeV and 0.55 MeV respectively. You have to find out the location of the Fermi level at 300 Kelvin, and Me is the rest mass of an electron, which is a constant, and band gap is also given to you. You have to find out whether this particular Fermi level, like where this particular Fermi level lies between the convection band and valence band. So that is what, like suppose you will be getting something like EC minus EFI or EV minus EFI is equal to so and so value. So you will be able to take, suppose it is EC minus so and so is your EC minus EF is so and so, which means that EC is higher. So we can say that the Fermi level lies X value below the conduction band, or it is Y value above the valence band. Like that your options are given. 0.54 and 0.55 are the 45 are the options, but you have to find out whether it is above the valence band or below the conduction band. The effective masses are given to you. You have to find out location of the intrinsic Fermi level at 300 Kelvin. Me is a constant. Band gap is given to you as 1.1 electron volt. Okay, somebody has answered in the chat box. Let us check what it is. Okay, location of the okay, fine. Closest answer is 0.54. 0.54 above. Okay, can you like Surya Teja? Can you complete the answer? 0.54 above what? Valence band. I hope. Location of the intrinsic valence silicon is 7.5 below conduction band. Okay. Okay, 0.54 below conduction band is the option that I got. 0.54 below conduction band. 0.54 above valence band. Okay, both answers are here, so just wait and see. Option A. One person has mentioned option A. There is another argument of option B. Okay, let us wait for a few minutes and then we'll find out. Okay, so we have two equations for this. So to finding out the Fermi level where it lies, we have either with respect to the valence band we can take, or with respect to the conduction band we can take. So valence band plus Eg minus 3 by 4, or conduction band minus the whole of half of each E by 2 plus 3 by 4 KTLN ME by MH. So here I'll be using the first equation, that is with respect to the valence band. So effective masses of electrons and holes are given as 1.10 Me and 0.55 Me, and band gap is also given to you. So while substituting this band gap value, we have 1.1 by 2. Rest of the things we can directly substitute 3 by 4 Kp. And since I am substituting in electron volt itself, I am taking 8.617 into 10 to the power minus 5, 300, which is the temperature, Ln 0.10 Me by 0.55 Me. So which upon solving will give me as EF minus EV is equal to 0.5356. So 0.54. EF minus EV is equal to 0.54, which means that the Fermi level is higher and the valence band is below that. Right. EF minus EV is a positive value, which means that Fermi level lies above the valence band. Therefore, 0.54 above the valence band, H is the answer. Suppose you are using the equation using EC, what happens is that you will get EC minus EFI is equal to negative 0.54. So you will have to rephrase accordingly. So with EF minus EV, you will get a positive value. With EC minus EFI, you will get a negative value. So when that negative is brought to the other side, we can find out the Fermi level lies below the conduction band and above the valence band edge. So 0.54 above the valence band edge is the right answer. I hope it's clear to you now. Is it clear? So I hope it's clear.
Yes, ma'am.
Yeah. Okay. So in that case, let us go to the next question. So here it comes like this. See, EFI minus EV is equal to 0.54. So above 0.5, above valence band, it lies at a distance of 0.54 electron. Yeah. So which of the following materials can be considered transparent to visible light? Silica, silicon, cadmium sulfide, gallium arsenide. So for finding the answer to this, you need to check out the band gap of these following materials. So you can use your online sources and find out the band gap of silica, silicon, cadmium sulfide and gallium arsenide. So once you know the band gap, you know that the band gap is the minimum energy that is required for activating electrons. So which of these materials are considered transparent, that is does not absorb, actually allows the radiation to pass through it. So everyone please find out the band gap of silica, silicon, cadmium sulfide and gallium arsenide. Okay, somebody has answered. Silica, one person has answered. Okay, we'll wait for the others. Okay. see if there are other answers. Silica, silica, okay, silica and CNG, okay. So in that case, so band gap is basically for silica it is 7.5 to 9.6, silicon is 1.1, cadmium sulfide is 2.42, and gallium arsenide is 1.42. So suppose you have, say, for this case of silicon, silicon is 1.12. So an easy way of finding this is lambda is equal to, in order to find out which wavelength can be transmitted, which cannot, whatever band gap value is given to you, suppose for silicon is 1.10 or 1.12, you divide 1240. So this is basically the relation E is equal to Hc by lambda. So from that, Hc, this constant in nanometers, is 1240. So lambda in case of silicon will come approximately to what value? 1240 divided by 1.12. That will be 40 divided by 1.12. Approximately we have 1107 nanometers. So this 1107 nanometers is our threshold. So here what happens? 1107, after 1107 the cutoff will start happening. So this is the, so suppose you have a band gap value, and this band gap value will be converted into a particular wavelength, and all the wavelengths below 1107 will be absorbed. Only greater than that will be allowed to transfer through. So that is because you have a semiconductor material. That semiconductor material has a band gap. So any energy greater than or equal to the band gap will be absorbed by the material for creating electrons and holes. So 1.10, 1.11, 1.12, all these values will be absorbed. That energy will be absorbed, which means that all the wavelengths below that threshold value will be absorbed, and all wavelengths above it will be transmitted through. So for in the previous slide we had seen the values for cadmium sulfide, gallium arsenide, and silica as well. So when we are converting this according to the equation 1240 by 9.6 or 1240 by 2.42 or 1.42, we get that all wavelengths below 873 will be absorbed for gallium arsenide. For cadmium sulfide it will be 512, and for silica all wavelengths below 165 will be absorbed. So our initial question was, which of the following can be considered transparent to visible light? That visible range will be 400 to 700, right? So which of these following materials actually allows the 400 to 700 to pass through? Gallium arsenide doesn't. Cadmium sulfide doesn't. And silica in that case only below 165 will be absorbed, rest all will be allowed to transfer. So since silica can absorb only up to 165, so from say 100 to 165 it will absorb, 165 to like the entire solar spectrum it will allow to pass through. That is why it allows the major part of the visible spectrum to be transmitted. So once more I'll repeat. So whenever you have a material, you have something known as the band gap, which is the minimum energy that is required for creation of electrons and holes. So this particular band gap energy can be converted into wavelength using the relation 1240 divided by the energy value. So suppose I am supplying 1.10 electron volt to the material. There will be a wavelength corresponding to that. In our case, it's 1107. If we supply 1.10, 1.11, 1.12 or any higher values of energy, all that will be absorbed, meaning that all wavelengths less than that 1107 will be absorbed. So in our case, we had options between silicon, silica, cadmium sulfide, and gallium arsenide. On converting these energy values into lambda for gallium arsenide, we saw that below 873 everyone will be absorbed. Cadmium sulfide below 512 everything will be absorbed, and for silica only below 165 will be absorbed. They are asking which of the material is transparent to visible. Visible actually lies from 400 to 700, and in that case 400 to 700 is freely transmitted by silica. This is because only less than 165 it absorbs, the rest all it allows to pass through. That is the ratio. Therefore silica will be your answer. So is that clear to all of you? If you have any doubts, please ask now. So is it clear? Any other questions or anything from that? So let me check if anyone has any doubts. Okay, I hope no one has any doubts on that. In that case, let us move to the next question. Okay. In an intrinsic semiconductor, Nc is greater than Nv. Where is the Fermi level located at room temperature? Take Eg as the band gap. All choices are given with respect to the top of the valence band. Okay, so it's an intrinsic semiconductor. Intrinsic semiconductor at room temperature, it is not absolute zero. It is at room temperature, and at room temperature, Nc is greater than Nv is the condition. Then Eg is the band gap, and you have to find out where the Fermi level is located. All choices are given with respect to top of the valence band. So here top of the valence band, meaning that EV will be the top of the valence band, EV will be considered as your starting energy or zero energy. So all measurements will start from there. So if Nc is greater than Nv, where does the Fermi level lie at room temperature? We know that at absolute zero, the Fermi level should lie midway between in valence band and conduction band. So that is not the case here. It is Nc greater than Nv. So then what is the location of the Fermi level? Okay. So option A. Okay. The person has given us option A. Let's wait for the others. option B. Okay, one person has mentioned option A, another person has mentioned option B. Okay, what about the others? So, the answer. So basically, we know that EFI is equal to EV plus half of EG minus half of KBT ln NC by NB. So NC by NB will be, it is given that relation between NC and NB is given as NC greater than NB, which means that NC by NB will be greater than 1. So therefore the Ln value will be positive. If top of the valence band is considered as reference, then valence band energy, as I mentioned, will be 0. So this EV value will become 0. Therefore basically we have Eg by 2 minus half of some positive value. Therefore Fermi level, so Eg minus half of some constant thing. So which means that Fermi level is located below the Eg by 2. That is why. So once more I'll tell you, NC by NV is greater. So which means that NC by NV will be a value which is greater than 1. So which this entire term becomes something positive. And all choices are given with respect to top of valence band is the option, which means that EV value will be 0. Therefore your Fermi intrinsic will be half of EG minus some constant value. So EG by 2 will be there, half of that EG. Less than that, some constant value has to be taken so as to reach your Fermi level. So basically, it is below Eg by 2. Option B will be your answer. So is that clear? So someone was mentioning it as option B. Yeah, so Grace has mentioned it as option B. So option B will be your answer. So is that clear for all of you? I hope it's clear. So it's basically using the equations itself. Nothing more than that. And here you have to be careful. It is with respect to top of the valence band. So EV is equal to 0. Suppose you are using EC, then you're from valence band again you have to go for another calculation so as to reach EC. So since it is mentioned with respect to top of valence band, you have to opt for the equation which involves intrinsic level EV, EG and NC by NV. So I hope it's clear. So we can go to the next question. So for an intrinsic semiconductor, the room temperature electrical conductivity is given as 10 power minus 6 ohm inverse meter inverse. If electron and hole mobilities are 0.75 and 0.06 meter square the volt inverse second inverse, then intrinsic carrier concentration per meter cube, your Ni value has to be found out. It is an intrinsic semiconductor. There is only thermally created electrons and holes. No additional dopants are there. Conductivity value is given to you. Then electron and hole mobilities are also given to you. You have to find the value of Ni at room temperature. So it's a very straightforward question. So you can try now. So has anyone posted the answer? Okay, nobody yet. So Am I audible? Like, is the screen visible and am I audible?
Yes, ma'am.
Yeah. In that case, I'll go to presenting the answer. Yeah. So basically, it is given that conductivity is given, electron and hole mobilities are given. Somebody just posted something, 7.71% has answered. So let us see. Yeah. So this is the equation that you have to use. Conductivity of intrinsic semiconductor is given by sigma, which is the conductivity, mu E plus mu H, E into Ni. Here everything else is given to you. You simply have to find out Ni. So conductivity sigma, that is 10 power minus 6, electron mobility is 0.75, mole mobility is 0.6, and while substituting you have to just add the charge of electron, that is 1.6 into 10 to the power minus 19 to it. Upon substituting everything, that is 10 to the power minus 6, the electron hole mobilities and the value of E, you get the value of Ni as 7.78 into 10 to the power 12 per meter cube, or to meter power minus 3. That is per meter cube. So 7.78 into 10 to the power 12 is your answer. So I hope it's very clear. It's a very direct equation, that is sigma is equal to mu E plus mu H, E into Ni. So with that, let us move to the next question. Intrinsic carrier concentration of silicon at 300 Kelvin is 10 to the power 10. That is, Ni is given as 10 to the power 10. A sample of silicon is doped with phosphorus atoms of concentration 15, 10 to the power 15, and boron atoms of concentration 10 to the power 16. Assume complete ionization. Which of the following is true? You have to find out N and P, that is the number of electrons and the number of holes in the material. So intrinsic value Ni is given as 10 to the power n, and the same Si will be doped with phosphorus atoms of concentration so and so, and boron atoms of concentration so and so. We have to find out which of these are true. Ni, what is the value of N, and what is the value of P. So we have the relation which Ni square is related to N and P, right? So using that, you have to find out. Anybody has got the answers? Okay, nobody so far. Let us wait for a few more minutes. Anybody? So otherwise I'll present the answers. So I'll go to presenting the answers. Okay. So here both P and N type is added. So this is something known as compensation doping. And if you see here, the concentration of Na, that is the holes are greater than Nd, which is now therefore we can say since Na is greater than Nd, it is a p-type semiconductor. That is because if we see here, the p-type boron atoms are 10 power 16 and the n-type phosphorus atoms are only 10 power 15. 10 power 16 is greater than 10 power 15, so which means that it has become a p-type semiconductor. And in p-type, the excess of p-type carriers is given by Na minus Nd, that is 10 power 16 minus 10 power 15, that is 9 into 10 power 15. So now we have to find out the carrier concentration, that is the n-type carrier concentration. So we know that Ni square is equal to n into p. So p value we have already got, the excess of p value is already with us. From that we can find out the n value. So from these options we can find out p is actually equal to 9 into 10 power 15 and n is equal to 1.1 into 10 power 4. So that will be our answer. So initially we have an intrinsic carrier. So in that intrinsic carrier, the value of Ni is given as 10 power 10. So it is doped with the both types of atoms. That is it is doped with a pentavalent as well as a trivalent impurity. So pentavalent impurity is only 10 power 15, whereas the trivalent one is 10 power 16. So it becomes a p-type semiconductor. The excess of p carriers is given by Na minus Nd, that is 9 into 10 power 15. So 9 into 10 power 15, we have two options here, that is B or C. Now we have to find out the value of n. From the relation Ni square is equal to n into P, Ni square is initially given to you, P value we have just find out. So from these two, we can find the value of n as 1.1 into 10 power 4. So option C will be your answer. So I hope this is clear. Yeah. So next question is intrinsic carrier concentration at 300 Kelvin for a silicon semiconductor is 10 power 10. Electron and hole mobilities are given to you. This Si is doped with the 10 power 15 phosphorus atoms and at 300 Kelvin the dopants are completely ionized. Then what is the electrical conductivity? So initially we had an intrinsic carrier. That intrinsic carrier we are adding pentavalent phosphorus atoms at in the range of 10 power 15 atoms at 300 Kelvin. Now we have to find out the electrical conductivity of this doped silicon. So initially we had seen conductivity equations for the undoped silicon, that is the intrinsic values we had seen. So here we have to find out the electrical conductivity to doped silicon. So for that we have to find out the new carrier concentration. So once you get the carrier concentrations, you can find out the conductivity. So can everyone start solving? So anybody has tried it? So shall I go to the answers or do you want some more time? Hello? Shall I go to the answers?
Yes, ma'am.
Okay. So basically here we know mu E and mu H is given to you, that is the mobilities of the electrons and holes. Then you have Ne, that is the intrinsic carrier concentration is given. So basically from that, sorry, the Ni intrinsic carrier value, that is Ni, is given to you, and also what is given to you, silicon is doped with 10 power 15 phosphorus atoms, that is the Ni value. N value is also given to you, 10 power 15. So from this Ni and N, you have to find the P value. We know that Ni square is equal to N into P. So Ni square 10 power 10 the whole square by 10 power 15. So P value we get as 10 power 4. So now we have N value, P value, electron mobility, hole mobility. So electrical conductivity will then be Ne mu E plus Pe mu H. So if you remember, you might have noticed that in case of an intrinsic semiconductor, it is Ni into E into the whole of bracket mu E plus mu H. But that is the intrinsic case. Now, since we are using a dopant here, the N and P values will also be present, and we have to account for those N and P values in the conductivity equation. So the conductivity equation gets modified as E, or also you can write as E into the whole of Ne mu E plus PH mu H. So on substituting all these values, you get 0.21627 ohm inverse centimeter inverse. So your answer will be option B. So in the upcoming problems also, as well as problems in the next class, we will be leaving intrinsic areas behind and we'll move on to extrinsic semiconductors. So when we are engaged with extrinsic semiconductors, always you have to account for the N and P, that is the number of excess electrons as well as the number of electrons as well as the number of holes in the system after doping. So that is why here Ni is given to you, N is given to you. You have to find out the P value, and using the N and P, you have to find out the electrical conductivity. So I hope it's clear. So next question is, in an extrinsic semiconductor, electron mobility due to impurity scattering is 300. centimeter square volt inverse second inverse, and mobility due to lattice scattering is 200. So what is the net mobility of these electrons in semiconductor? So this is based on a particular rule. So whenever you have an extrinsic semiconductor, there will be mobility due to impurity scattering as well as due to lattice scattering. So we had talked about lattice scattering earlier, right? So whenever there is more carriers, lattice scattering increases, therefore mobility decreases, and so on. So we had discussed. So suppose we have two components of scattering, that is the impurity scattering as well as lattice scattering. How is the net mobility of electrons in the semiconductors? So if you know a particular rule for this thing, you will be able to answer very directly. Yeah. So anybody has I'll just go to the answers. It's still loading. Yeah. So I think I'll go to the answer. Somebody has just option A. Okay, one person has mentioned as option A. So let us see. Yeah. So it's something known as the Matheson's rule, which means that the inverse of the overall electron mobility is given by, that is due to the inverse of the intrinsic scattering as well as the inverse of due to lattice scattering, where mu I is the mobility due to impurity scattering and mu L is due to the lattice scattering. So we have 300 and 200 respectively, and when you substitute in the Matheson's rule, we get 1 by 120. Therefore, mu E, or the electron mobility, is given. Net mobility of electrons in the semiconductor material will be given as 120 centimeters square v to the power minus 1 second to the power minus 1. So that is the answer. So this is the Matheson's rules. Whenever we have something, whenever we have doping, what happens is that there will be mobility due to impurity scattering as well as mobility due to lattice scattering. So they will have a parallel connection, like a big law, and therefore from the Matheson's rules we have 1 by mu E is equal to 1 by mu I plus 1 by mu L. So 120 is the answer. So next is, consider the electrical conductivity of a p-type semiconductor at low dopant concentration. Conductivity is given by E n mu E P mu H. So we had discussed this equation before, right? Whenever there is doping, we have N and P along with that, and therefore we substitute it and find conductivity. Now we have to find out hole concentration at which the conductivity will be minimum. So electrical conductivity for p-type semiconductor with low dopant concentration is given by so and so. From this equation, at what hole concentration will the conductivity be minimum? So I'll give you, it is related to finding out the local minima, global maxima type of concepts you might have come across in mathematics. It is similar to finding those things. So we might have found out how to find the local minima, global minima, etc. So this particular question is similar to that. It is a mathematical concept. Yeah. So anybody has come up with the answer? Okay. Then, okay. Yeah. So should I go to the answers or is anyone trying it? If you want, I can go to the answers. So shall I go to the answers?
Yes, ma'am.
So basically, so we are asked to find out the whole concentration at which conductivity will be minimum. So it is the whole concentration and you have to find the minimum value of conductivity. So what you have to do is that you have to take the derivative of sigma with respect to p and then equate it to 0. So if you remember in mathematics, if you wanted to find out the minima of a particular equation, what we used to do is that we will derive it, we'll take the derivative of it with respect to the variable and at which we want it to be zero, like minimum, and then we will equate it to 0. So here they are asking the whole concentration at which conductivity will be minimum. So therefore you have to take the equation for conductivity, then take the derivative of that equation with respect to p and finally equate it to 0. So when we are doing that, we have to find d sigma by dt. So E is a constant, we take it out. D by dp n mu E plus P mu H we have to find out. B and mu H again are constants. So we have to find dn by dp and dp by dp. So basically this n again we have to consider as ni square divided by p, because we know that ni square is equal to n into p. So from that n is equal to ni square by p. So E is a constant, it is already taken outside. Mu E will again take outside. Ni square is also constant. We have to take the derivative of 1 by p, which is minus 1 by p square. Then we have to take the derivative of dp by dt, which is equal to 1. Therefore, what happens in the whole bracket, we have E outside. Here ni square is a constant. Derivative of 1 by p is minus 1 by p square. Mu E again is a constant. Mu H is a constant. dp by p is equal to 1. Therefore, now we have got this term, this left hand term. Now we have to equate it to 0. On equating it to 0, what happens? E gets cancelled out. We have ni square by p square mu E is equal to mu H. So we have to find out the value of p. Taking this p to the other side, we get p is equal to what happens? Root of ni square divided by mu E into mu H. Therefore, P is equal to Ni into root of mu E by mu H. So, this is the whole concentration at which conductivity becomes minimum. So, basically you took derivative with respect to whatever variable is mentioned. Suppose if it was with electrons, you should have taken d by dn. Here we take d by dp because we have to find out the minimum whole concentration. So, this whole conductivity equation you have to take. We have to take the derivative with respect to p, and for finding out the minima you have to equate it to 0. While equating it to 0, you will get P is equal to Ni square root of mu E by mu H, and this is the whole concentration at which the conductivity of the p-type semiconductor, extrinsic semiconductor becomes minimum. I hope it's clear to all of you. Yeah. So in the examination, this derivation part they won't be asked. They can ask you a question where you have to find the value of P. So either you can do the derivation then and there itself, or if you are a person who can memorize well, you can keep a note of this equation as well. So this is the minimum hole concentration. Similarly, you can derive another equation for minimum electron concentration also. So if you can memorize those equations, well and good, but if you can derive on the fly, that is also good enough. Yeah. So next is consider the semi-log plot of carrier concentration versus inverse temperature for an intrinsic semiconductor. Slope of this plot is proportional to what? So Fermi level, work function, band gap, or electron affinity. Carrier concentration, that is Ni versus inverse temperature, and it is a semi-log plot. Then slope of this plot is proportional to dash. Yeah. So I'll give you a few hints. So intrinsic carrier concentration is basically Ni is equal to root of Nc and B e power minus Eg by 2 times Kb into T. So this thing we have to convert into equation for a straight line. So whenever we are converting that, what we do is we take natural logarithms on both sides. Root of ln Ni and root of e to the power that minus Eg by 2 times Kb into T, and we have ln root of Nc/Nv. So here it is mentioned that it is now it has become somewhat in the case of a semi-log plot, carrier concentration versus inverse temperature. Inverse temperature meaning that 1 by T, carrier concentration is ln Ni. So whatever x and y we have need is already here. And now you have to compare it with the equation for a straight line, that is y is equal to mx plus c, where m is the slope and c is the intercept. So if your x-axis is temperature inverse and y is the semi-log plot of carrier concentration, then ln Ni is y minus Eg by 2 times Kb into T will be your m, 1 by T will be your x, and root of ln Nc will be your intercept. So in that case, what is the slope then? Y is equal to mx plus c. Can anybody now tell me? I've already told the answer now. Okay, somebody just posted in the chat box. Okay, one person has mentioned Fermi level. Okay. Basically, it's the band gap. It's not the Fermi level, because it should have been Fermi level is denoted by EFI, right? According to this equation, Eg is the band gap. Therefore, comparing with y is equal to mx plus c, mx is equal to minus Eg by 2 times Kb into T. At a given temperature, 1 by T is our x-axis over here. Minus Eg by 2 times into Kb, 2 times Kb is a constant. So it's inversely proportional to, it is proportional to minus Eg. Therefore, slope is proportional to the band gap. If it was something like EFI, it would have been Fermi level. It is not Fermi level here, but instead it is the band gap Eg. Only thing is, whichever equation is given to you, you have to take log on both sides, then it will convert to the form of y is equal. If it suppose a is equal to b into c, if you put semi natural logarithm on both sides, it will automatically convert to y is equal to mx plus c. And from that y is equal to mx plus c, they are asking us what is the m or the slope. So here it is minus eg. Therefore, it is proportional to the band gap. I hope it's clear. So next is molecular orbitals, or MO, are filled in the order of increasing energy. Which of these principles does not govern how the filling of molecular orbitals take place? So it is from a question from the previous week. So there are questions like, there might be questions like this in your examination. So that is why this has been included here. So molecular orbitals are filled in the order of increasing energy. Which of these principles does not govern how the filling of molecular orbitals takes place? It comes from your basic chemistry understanding. So we know that 1s1, 1s2, like 2s1, 2s2, 3p1. So it doesn't go in the numerical order. It goes according to the energy order, right? So which of these doesn't affect that? That is the question. Which of these principles does not govern how filling of molecular orbitals take place? That is the question. Okay, somebody just posted the answer. Option A, okay. Anybody else? Okay, in that case, I'll go to the answers. Since we are shooting time, I don't want to keep you guys waiting, so I'll go to the answers directly. So Hund's rule, we know that what has to be done. So suppose the molecular orbitals are filled in with 1s1, 2s2, 2p has to be filled simply before directly occupying them. That is the Hund's rule. So Hund's rule is important. Pauli's exclusion principle states that no two electrons can have identical quantum numbers. Therefore, that is why these orange and blue are different. At least the spin quantum number should be difficult. So in other words, no more than two electrons can occupy the same orbital. Two electrons must be having opposite spin. That is what the Pauli's exclusion principle says. So it's not Pauli's exclusion principle. It's not Hund's rule. Next is, yeah. So this is what Pauli's exclusion principle gives us. So it cannot be of the same spin. So now we have Madelin rule. Madelin rule basically tries to tell us the order in which electrons fill energy sublevels of atoms. Hofburg principle states that in ground state, electrons occupy lowest energy sublevel. So Madelung rule also tell us how the energy filling takes place inside atoms. So that is what governs the Aufbau principle, which then says that in ground state, electrons will always occupy the lowest available energy first. So according to the Aufbau principle is how we decide how that order goes. 1s1 will come, then 2s2, then 3, then 2p, then 4s, then 3p. That is how the order goes. It's not like 1s, 2s, 2p, 3s, 3p, 3d. This according to how these arrows move, that is how the filling takes place. That is given by the Madelung rule and Aufbau principle. So basically, Heisenberg uncertainty principle tells that it is impossible to measure or calculate exactly both the position as momentum. So this actually is based on the dual nature of matter. It is so here you have to note that it is associated with the formation of molecular orbital but not filling of the molecular orbital. So the answer to our question is Heisenberg's uncertainty principle. Pauli's explosion principle, Aufbau principle, Madelung rule and Hund's rule, all of this tell us how the molecular orbitals are filled, how the electrons occupy the energy states. But Heisenberg uncertainty principle helps us in understanding how the molecular orbitals are formed, but not how they are filled. So the answer is Heisenberg's uncertainty principle. So I hope that also is clear to you. On that note, let me stop today's session. So we have short time a little bit. So from next session onwards, I'll try to keep it restricted to 2 hours so that you can attend to your other works. So thank you everyone for joining. If you have any questions or doubts related to this 2 weeks, please do mail me at sandra.pmr@iitm@gmail.com or post your additional queries in the discussion forum. And whatever material we have been presenting here, that will be made available to you within the NPTEL team. I have been getting requests from people for getting permission for editing and downloading the PPTs. Usually this doesn't happen. It will be by default given to you. I don't know why this time it's happening. So I hope today's session was useful to you guys. So on that note, let me conclude for today. Thank you everyone for joining. So see you next week. Thank you and have a great evening. Thank you so much. Yeah, you guys can leave now. Yeah, thank you.